Yes, so this is all forward-looking. Everything with Monte Carlo so far, you have to wait until the end of the episode to see the return that you got, and then you have to go back to the state that you want to update and say, okay, well, from that state, I ended up getting 100 points of reward, and now you update your estimate from at the end of the episode. So this is one disadvantage of Monte Carlo that we'll address shortly. Okay, so really what we're going to move towards then is we want to move towards algorithms that don't have to maintain these statistics and just incrementally update themselves. And one way in which this can be done is actually by forgetting old episodes. So you don't necessarily want to take a complete mean. Sometimes you actually want to forget the stuff that came a long time ago. And one way you can do that is just by having a constant step size here. And this gives you like an exponential forgetting rate when you're computing your mean. It gives you an exponential moving average of all of the returns you've seen so far. So it's another way to compute a different type of mean now, where we've replaced our 1 over n by this fixed step size alpha. But the concept is still the same, that we had some estimate of what we thought the mean value was going to be. Then we saw some return from that state onwards. That gives us an error term. And now we just move our value function a little bit in the direction of that error. So now we don't move all the way to correct this exactly to the overall mean. We maybe under or overcorrect, depending on what the value of alpha is.
But the only thing which we got here is like we don't have to store one integer, right? Which is n. So it's not a huge advantage.
So the question was, is there an advantage to this beyond not having to store n? So maybe I wasn't clear. So first advantage of this approach is that this applies to non-stationary setups where things can be drifting around. So in the real world, stuff is changing. You don't want to remember everything all the way into the past, because stuff that came 100 years ago you kind of want to forget about, and including that in your mean is just going to slow you down and sort of give you baggage that you actually want to let go of. And we'll actually see as the lectures develop that we're always in that case in reinforcement learning. We're always in the case where things are non-stationary, because although in this lecture we're evaluating a fixed policy, in general we'll start to improve the policy, and so the thing which we're evaluating is getting better and better and better. And so that's why we prefer these non-stationary estimators rather than taking the true mean. In addition, it's something where we can have memoryless algorithms where a new step comes in, and we just look at that step and we can do an update without having to track these statistics about what's come before. I think that's a less important detail. So we're just in this setup where we're looking at algorithms where we move a little bit towards the sample that we've seen. Okay, so that's Monte Carlo learning. So very simple idea. You run out episodes, you look at those complete returns that you've seen, and you update your estimate of the mean value towards your sample return for each state that you visit. Okay, now we're going to move on to a different class of methods which really do now break up the episode and use incomplete returns. So let's think about this. What do we mean by temporal difference learning? So again, like Monte Carlo learning, these methods, TD methods we call them, they learn directly from actual experience, from interaction with the environment. It says episodes here, actually TD applies to the non-episodic case as well, continuing case. TD again is model free, so again we don't need to know how the environment works, the transition structure, the reward structure. Again, we don't need to know how the dealer works or the deck of the cards, or any of those details. But one difference from Monte Carlo is that now we're going to learn from incomplete episodes. So we don't have to go all the way until I hit the wall and see how much reward I got from that complete trajectory. I can basically take a partial trajectory and now use an estimate of how much reward I think I'll get from here up until the wall in place of the actual return. So this idea is called bootstrapping, this idea of substituting the remainder of the trajectory with our estimate of what will happen from that point onwards. That's called bootstrapping, where we basically update our guess of the value function. So I'm going to start off guessing how long it's going to take me to get to the wall. I'm going to walk some number of steps. I'm going to make another guess of how long it's going to take me to get to the wall. And I'm going to update my original guess towards my subsequent guess. That idea is called bootstrapping, and that's the fundamental idea behind TD learning. Okay, so let's make that more concrete. So again, the goal is the same as we had before. We're trying to learn our value function, v pi. We're just doing policy evaluation in this class. The next class will turn this into a control method. And we're just going to look at our interactions under some policy. So if I follow my random walk around, how well will I do? How much reward will I get? And I want to estimate this efficiently. And now we're going to try and do this online. We're going to try and just look every step. I'm going to make a new estimate, adjust my estimate of the value function without waiting until the end. So let's think about what we've done so far. So in Monte Carlo, what did we do? Well, we were in some state. We had an estimate of the value function. This was our previous estimate of the value function. We got our return. We looked at the error term between our estimated value and the return, and we updated our value function a little bit in the direction of that error. So what we're going to do now is we're going to use temporal difference learning, and let's consider the simplest version, TD0. We'll understand later what that 0 means. But what this means is now we're going to update our value function towards the estimated return after one step. And I'm going to estimate how much the return is going to be. And our estimate basically consists of two parts, just like in the Bellman equation. So the estimate consists of two parts, which are the immediate reward. So I think the total reward is going to be the immediate reward plus the discounted value of the next step. So it's just like the Bellman equations we saw in the previous lectures. And now what we're going to do is we're going to substitute this estimated return, and we're going to use that instead of the real return. So we're basically going to take exactly the same algorithm we had before. We're going to pull out the real return, and we're going to replace it with an estimate of the return, which consists of these two pieces, the immediate reward plus our estimated reward over the rest of the trajectory. So we're coming up with an estimated biased algorithm, and we'll see the consequences of that bias shortly. Okay. So this term here, this red term here, is what we call the TD target. This is the thing which we're now moving towards. It's like a random target. It depends on exactly what happens over this next time step. But we get some immediate reward and some value at wherever we happen to end up, and we're going to move towards that thing, and that thing's called the TD target. And this whole error term here, the difference between what we thought we had and the difference between our TD target and our estimated value before we saw this step, is called the TD error. The difference between our estimate before and our estimate after taking a step. That's the TD error. So why is this a good idea? I mean, I think the simplest example would be, imagine you're driving along, you're driving in your car, and if you're doing Monte Carlo learning, you have to basically, when would you update your value function? Well, imagine that you drive along, and consider the following scenario where you're driving, you see suddenly a car that comes hurtling towards you, and you think you're going to crash, but then you don't actually crash. At the last second, the car swerves out of the way, and you don't actually crash. So in Monte Carlo, you wouldn't get this negative reward. You wouldn't have a crash. You wouldn't be able to update your value to say that you almost died. But in TD learning, you're in this situation where you think everything's fine. Then you drive along, and you're now in a situation where you think you're going to die. You think this car crash is going to happen. And so you can immediately update the value you had before to say, oh, that was actually worse than I thought. Maybe I should have slowed down the car and anticipated this potential near-death experience. And you can do that immediately. You don't need to wait until you die to update your value function. So there's a great slide by someone I know in reinforcement learning. He puts up these backup diagrams that we saw in the last class, and with this big skull and crossbones saying, you can't back up death. Anyway. So let's do another driving example. So this example is from Sutton and Bartow, so you can look at this in your own time. But the idea is basically that, I'm driving along, I'm on my way to work. Let's imagine I didn't actually do my usual horrible commute on the train and was actually in a car. So I start off by making some prediction of how long it's going to take me. And so these rows basically show how much time has passed so far, how much time I think it's going to take from this point onwards, and the total of these two columns here, time so far plus predicted time to go. Okay, and I start off thinking it's going to take me half an hour to get to work. But maybe then I leave the office and I reach the car and I see that it's raining, and I'm like, oh, I'll have to drive a bit slower, there'll probably be more traffic. Took me 5 minutes, and now, okay, maybe I haven't really adjusted I now think it's raining, so it's going to take me slightly longer. So I think it's going to take 35 minutes to get to the office now, giving a total of 40. Next step, I get off the highway, and that's taking me 20 minutes. And now I think, okay, that went a bit smoother than I expected, so now I think there's only 15 minutes to go, giving a total of 35. Then I get stuck behind a truck and think, oh, actually it's going to take me a bit longer than I thought, so now I kind of increase this. Think, oh, there's actually 10 minutes to go now, it's going to take me 40 minutes. And then I get on the home street, and I've only got, things are going okay, but it took a little longer than I thought. I think there's still 3 minutes to go. And then eventually I get there, and it actually took, in total, 43 minutes. I realise there's no more time to go, and so the total, everything lines up at the end, and we think that there's nothing left, and it took us 43 minutes in total. So now how would we actually update our value function based on this trajectory of experience? So these figures really show the difference between Monte Carlo and TD in practice. And in Monte Carlo learning, if we look at each point along that trajectory, this shows basically how much, like the total predicted journey time, so basically what we thought, so it actually took 43 minutes along here, but at every moment I had some prediction of what that total time would be. So here I thought it was going to take 30 minutes, it actually took 43. Then it was sort of, I reached the car, and at that point I thought, uh-oh, it's going to take 40 minutes, and then things were going better, so I thought it's going to take 35 minutes, and so forth. And at each step along this, using Monte Carlo learning, you update towards the actual outcome. You have to wait until you finally get there, see that it actually took 43 minutes, and then update each of your value estimates along the way towards that 43 minutes. Okay? Whereas with TD learning, it's quite different. At every step, it's like you started off thinking it was going to take you 30 minutes. After one step, you thought it was going to take you 40 minutes. So you can immediately update there already. You don't need to wait until anything else happens. You can say, oh, I was in a situation where I thought it was going to take 30 minutes, but then I saw it was raining, so probably my 30-minute estimate was too optimistic. Let's adjust that a little bit towards 40 minutes. At the next step, I started off thinking it was 40 minutes, but then things went quite smoothly on the highway, so I can immediately pull this guy down and say, well, maybe I was a bit pessimistic and I should move this towards this guy. And then, you have to realise that you might get stuck behind a truck, so that might pull you back up again, and so you should move this towards your subsequent estimate. And eventually you get grounded by the actual outcome. So you're always updating guess towards a guess, but eventually you get grounded by this actual outcome where you really get there, and that's the end of your episode, and you get your real reward of having a day at work.
Can I just check, in this example, what is the goal and what are the actions?
So first of all, okay, the goal is so the reward function is the time that it takes you. So think of that as the reward function. So the reward function is time. So you could think of this as the goal is to get to work, and you get -1 per step. So if you made all of these negative, you could think of that as a goal, and that would be a well-formulated Markov decision process such that the optimum corresponds to getting to work as quickly as possible. The actions there are no actions here. Think of this as a Markov reward process. We're just trying to do policy estimation. The policy could be anything we want. The policy is just driving your car, and the action space it could be anything. And the reason it doesn't matter is we're just trying to evaluate whatever that policy is and whatever that action space is. For now, we're just looking at how to evaluate how much reward I got from this particular trajectory. Remember, you can flatten any MDP into a Markov reward process given a fixed policy. That's kind of what we're doing. We're just evaluating this thing. We're just trying to understand how much reward you get, independent of the action space. Next class, it will matter much more what the action space is, because we're going to pick actions so as to optimize our decisions. Okay. So is this a good or a bad idea? So, well, there's several ways in which it's a good idea. So the one we've just seen really and focused on is that TD can learn before you see this final outcome. So you don't need to wait until you crash and die. You can already start learning after just one step. Whereas Monte Carlo has to wait always until the end of the episode before you actually see the return, and then it backs it up retrospectively. And one advantage of this is that TD can learn in situations where you never see the final outcome. So this basically means, what if you get incomplete sequences? What if you're learning from in some situation where you just don't get to observe the return at the end of the episode? We'll see this later when we do off-policy learning. This really happens a lot in many cases. Or what happens if you want to deal with continuing environments that just go on and on forever and you never get to the end? Well, Monte Carlo just doesn't apply there. I mean, you can go to some arbitrary horizon in the future and just back up from there, but there's always some error introduced. whereas TD really works. It really works in all of these cases. Even if the environment just goes on and on and on, you just update now from what happens at the next step. And if your steps go on forever, that's okay. Everything still works. You'll find the true value function regardless. Okay?
And does it learn the same behavior? So if you have a car, and the car almost crashes, but it doesn't. And the reason that it doesn't is because other people avoid a lunatic. So when you're learning step by step, you're going to learn a behavior that you're scared of crashing. But if you only learn from the very end, you would never learn something which encouraged you to avoid your own manic behavior, because by the time you get to the end, you don't suffer the consequence.
So it learns. We'll answer that question properly. It does. So the answer to that question is a really good question. Does TD find the same answer as Monte Carlo? We're going to start to address that. The basic answer is that that TD finds the true value function. It finds the true value function. As long as you run this thing out, it will always ground itself, because even though you correct yourself based on your guess, and that guess might not be right, that guess will then be updated towards something that happens subsequently, which will ground it more and more. So all of your guesses are progressively becoming better, and that information backs up such that you get the correct value function. So it's fine. Okay. So we're trying to understand the pros and cons of TD compared to Monte Carlo. So one other issue which comes up, which is a major difference between the algorithms, is this bias-variance trade-off. So the return, this sample that we get of all the rewards in the episode, we can think of in Monte Carlo, this return that we used. So in Monte Carlo, we just used this whole sequence of rewards that we actually sampled from our MDP, and that's an unbiased estimate of the value function. So the value function is just, the definition of value is the expected return. So that's what we mean by unbiased, that this is just a sample of this expectation. So if we actually update towards the return, we're not introducing any bias. The law of large numbers will take effect. We'll really find the true value function. Everything is good. What if we were to use the true TD target? By true TD target, we mean that we drop in the true value function. Like if some oracle told us the true value function, and we used the immediate reward plus the true value at the next step, that would also be an unbiased estimate of the value function. And we know that from the Bellman equation. The Bellman equation tells us that the value function is equal to the expected reward plus discounted value at the next step. That was the Bellman equation, the Bellman expectation equation from lecture 2. Okay, so either of these cases gives us an unbiased estimate. But what we actually do in TD is we don't use the true value. We don't have an oracle to tell us the true value. So what we substitute in is our best guess so far of what that value function is at the next step. So the target which we move towards, the target which we're updating our value towards, like I think I'm in some value, and I update towards the immediate reward that I got over that step, plus the discounted estimated value at the next step according to my current estimate. So now we've introduced bias. Like this estimate could be anything. Like I could be wildly wrong. I could initialize with some crazy value for this thing. So we introduce bias into our estimate, into our target, but we reduce the variance. So the TD target is biased, but it's much lower variance than the return. So intuitively, why is it lower variance? Well, let's look at the return. The return depends on, this random variable here, depends on the immediate reward after one step, and then whatever the environment does, it will take us to some next state. There's noise in that transition. There's noise in the reward we'll see here. There's noise in the next transition. There's noise in the reward we get here. There's noise in all of that whole trajectory of many, many random variables depending on the environment and the agent's policy over many, many steps. There's a lot of noise. It multiplies out over the course of the trajectory. Whereas the TD target, we only incur noise from one step. There's one step of noise in the reward we see. The environment gets to take one turn. We get one random transition, and then we invoke our value function at that next step. So this thing is much lower variance than this thing. We're only looking at the noise over the first step rather than over the entire trajectory.
But your estimation of the V as t plus 1 is a very noisy estimation.
It's not noisy, it's biased. So it's biased. You have some estimator of V, which may be wrong. It may not have the true value, but it's not noisy. This is at any given time. This is just some fixed function that you're looking up the value. So it doesn't depend on. So the state that you see is noisy, but the value function that the bias comes from the fact that your value function, the bias comes from the fact that this is not equal to this. Okay, so Monte Carlo is high variance but no bias. So some good things about Monte Carlo is, as a result of being zero bias, it has very good convergence properties. You know, we'll see later, even when you use function approximation, Monte Carlo just works. It works out of the box. Everything, all the algorithms just converge to the correct answer. It's not very sensitive to the initial value because we're not bootstrapping from the initial value. It will just, you know, it still matters where you start. It will take longer to adjust a really wildly wrong value towards the correct value. But it doesn't kind of cycle off itself. It doesn't feed off itself. It's very simple to understand and use. So TD, on the other hand, is much lower variance, but it has some bias. And so you should be wondering, well, does the algorithm even work if it's biased? And the answer, luckily, is yes. And it's usually much more efficient than Monte Carlo because it's so much lower variance. In most situations, TD, we'll see examples of this, TD is generally a much more efficient algorithm. And for the special case we're looking at, policy evaluation using table lookup, it converges to the true value function. So this is true. I'm not going to prove it, but this was proved actually by Peter Diane, was one of the first people to prove this for the general case. But not always with function approximation. So there are cases, which we'll see, there are special cases where the bias in TD leads to the algorithm not behaving in the way that we would like. But these are quite specific cases that we'll start to address in the next couple of lectures. And it's more sensitive to the initial value because it is feeding off itself in this way. Okay? Yeah, question?
What do you mean, which function you mean by this function approximation?
Okay, so in a couple of lectures' time, what we'll see is that everything we've done so far is not practical because we're estimating the value function V of S for all states separately. And in most interesting problems, you've got more states than you can count. And so what we'll do is we'll use a function approximator to estimate the value function later. And the question is, do these methods still work effectively? And the answer is yes, except for certain specific cases that we'll deal with. Okay, let's make this a bit more concrete with an example. So this problem here is a random walk. So what's happening in this problem? It's like one of the simplest MDPs you could imagine. In fact, it's just there are two actions, left and right. We're going to consider a uniform random policy that goes left 0.5, right 0.5. If you end up in this state here, the episode terminates and you get net zero reward. These are the rewards you get for the transition, so 0 reward, unless you make it all the way to the right, in which case you'll get a reward of 1. So you're just going to do some random walk along here. If you end up here, that's good, episode finishes with a reward of 1. If you end up over here, that's bad, you get 0. Okay, and then the question is, well, what's the value function for this thing? You know, what's the value of being in each of these states? And we could just use this to get an intuition of, you know, the simplest possible case to get an intuition of how Monte Carlo and TD compare to each other. So if you use, if you actually look at the value function and apply TD, so this is applying the TD0 algorithm, what you see is that you can start off with some completely arbitrary value estimate. So let's start off initializing everything to, say, 0.5. And then if you run this for 1 episode, 10 episodes in blue, 100 episodes here in black, we see that this thing starts to flatten out onto what actually is the true value function, which is this straight line up here. Okay, so roughly 100 random episodes here, and you've pretty much got the value function using TD0. So how does that compare? So intuitively, that's basically saying that, you know, state A, the value kind of increases as you move towards the 1. So you basically, I think the true value function is something like 1, 6, 2, 6, 3, 6, 4, 6, 5, 6 as you move along. That's the true value function, which you can find by dynamic programming. Okay. So now, what happens if we compare Monte Carlo with TD? You know, is it really true that TD is more efficient? So here we're just looking at the number of episodes that so this is like picking out at each of those stages, like 1, 10, 50, 100. And now we're plotting these learning curves, showing how the error reduces in the value function. So what we're looking at on this y-axis is basically the mean squared error, the root mean squared error, averaged over all states. In other words, we're looking at the total error between the true value function and the value function that we've estimated after some number of steps. We're looking at the sum squared error and then take the square root of all of that. Okay, and then what we see is that if we look at in the black lines here, we have Monte Carlo learning with different step sizes. And in grey here, we've got TD learning with different step sizes. And so this is for a small number of episodes. Actually, this same result extends out further. You just have to optimize the step size, and you'll see that, you know, for appropriately chosen step sizes, TD continues to do better than Monte Carlo. So you see this, basically this is showing us the effect of bootstrapping. That by bootstrapping you can learn much more efficiently than incurring the variance of all of this things which come later on in the episode.
Is there any reason that the error stopped growing when we increase the number of episodes?
I think it's just the noise in these step sizes are very high. So with these step sizes, you can never get exactly to the true value function. So with a large step size, you basically will oscillate around the true value function within some ball that's governed by the size of your step size. So you don't guarantee to converge all the way to the optimal solution. So if you could, so the convergence proofs for TD actually use a decaying step size schedule using like Robbins-Monroe conditions, where you have to kind of do a sort of 1/n that kind of schedule for the step size, and then it really does converge. Same is true for any gradient-based method, you know, Monte Carlo. You would still need to, in many of the cases that we'll see, you still need to decay the step size according to an appropriate schedule. So I don't think it's actually, if you were to plot this out, I don't think it's going up. I just think it stabilizes in that, you know, you're only going to get within whatever accuracy your step size is. If you're jumping around too much with your steps, you can't expect to converge exactly to the right solution. You have to start reducing your steps to get exactly there. Okay. So we've seen so far that these approaches converge, both the Monte Carlo and TD we converge. We find the true value function as you add in an infinite amount of experience. But what happens if we were to just stop after a finite number of episodes? If we were to just show 3 episodes to our system and then keep iterating on those episodes and learn again and again and again, apply our updates, like repeat those episodes and just keep going over that same data again and again, what would happen if you applied either Monte Carlo or TD? Would they find the same solution? So to get an intuition into that, we will take a very simple example. So this is the AD example. So it's just an MDP with 2 states, A and B, and each row is a different episode of experience that we've seen. So in the first episode, you start in state A, you get a reward of 0. Then you go to transition to state B, and you get a reward of 0, and then the episode terminates. The next episode, you start in B, you get a reward of 1. Next episode you start in B, you get a reward of 1. Scroll down here, you see an episode you start in B and you get a reward of 0. So the question is for you guys, what's the value function? So any suggestions? What's the value of A and B? So let's do the easy one first of all. What's the value of B? So we've got 6/8. Right, so we've got 8 episodes starting from B. 6 of them got a value of 1. 2 of them got a value of 0, so I think everyone would agree the value is 6/8 or 0.75. What about the value function from A? Any volunteers?
16.
Okay, we've got one person says 6/8. Any other guesses? 0? Okay, so who thinks 0 and who thinks 6/8? Let's have a show of hands for 0. Okay, who thinks 0.75, 6/8? Okay. Good, about, of the people who said, about half and half. So those are respectively the Monte Carlo and the TD solutions to this problem. They're both perfectly legitimate solutions, and we'll see why. So first of all, the 0 answer I think is you know, the 0 one's easy to explain. We've seen one episode from A, and we got 0 reward on that episode. The return was 0 from this point onwards. So the value function, legitimately, we could estimate as 0 from that point onwards. Okay, that's the Monte Carlo estimate. We looked at complete trajectory starting from A. We had one complete trajectory starting from A, it got 0. What about the TD estimate? Well, implicitly, what this is doing is something like the following, which is it's building implicitly, imagine that you had tried to build an MDP model that models what we've seen so far. Okay, if you were to build an MDP to try and explain this data that you've seen so far, you would build an MDP model that looks like this. So you start in A, and 100% of the transitions that we've seen where we started in A transitioned to B and got 0 reward along the way. And once we got to B, 75% of the transitions gave us a reward of 1, and 25% of the transitions gave us a reward of 0, and then we terminated. So that MDP is the best explanation. So this is the maximum likelihood MDP that explains this data in the best possible way. Okay? So now we understand that, we can see what these guys converge to. So Monte Carlo always converges to the solution that minimizes the mean squared error. So it finds the best fit to the actual returns that we've seen. So if we saw these particular returns, Monte Carlo just minimizes the mean squared error over all time steps, all episodes. It minimizes the difference between the return that we saw and the value function, which we captured. Whereas TD0 actually converges to the solution of the MDP that best explains the data. So implicitly what TD is doing is it first fits an MDP, and then it solves for that MDP.